In the vast theater of the cosmos, countless objects are locked in an invisible gravitational dance. This cosmic ballet occasionally gives rise to a stunning phenomenon known as orbital resonance, a kind of synchronized choreography that shapes entire solar systems. So what is it? Imagine pushing a child on a swing. If you push at random times, you won't get very far. But if you time your pushes perfectly, giving a nudge just as the swing starts to come back down, each small push adds energy, sending the swing higher and higher. In space, gravity provides these periodic pushes. Orbital resonance happens when two bodies orbiting a central star have orbital periods related by a simple ratio of whole numbers, like 2:1 or 3:2. This means they repeatedly meet at the same points in their orbits, allowing their tiny gravitational nudges to accumulate over millions of years, dramatically shaping their paths. This can lock bodies into stable, protective patterns, or it can create chaos, flinging them into the cosmic void. Let's explore the different rhythms of this cosmic dance. The most common type is called mean motion resonance, or MMR. This is the direct ratio of orbits. For instance, in a 2:1 resonance, an inner body completes 2 orbits for every single orbit of an outer body. A perfect example of this is the relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes exactly 3. This is a 2 to 3 mean motion resonance. You might know that Pluto's strange, elliptical orbit actually crosses inside the orbit of Neptune. So why don't they ever collide? Because of this resonance. The precise timing ensures that whenever Pluto is inside Neptune's orbit, Neptune is always far away, in a different part of its own path. This gravitational lock has protected Pluto and a whole family of similar objects called Plutinos for billions of years. But not all resonances are about stability. In the asteroid belt between Mars and Jupiter, we see the opposite effect. The belt is not a uniform field of rocks. It has distinct gaps, known as the Kirkwood gaps. These gaps are zones cleared out by unstable mean motion resonances with the giant Jupiter. An asteroid with an orbital period that is, for example, exactly 1/3 of Jupiter's is in a 3:1 resonance. Every third orbit, it gets a gravitational kick from Jupiter at the same spot. Over time, these repeated kicks make the asteroid's orbit more and more elliptical, until it's eventually flung out of the belt entirely. The most prominent Kirkwood gaps correspond to these simple ratios: 3:1, 5:2, and 2:1 with Jupiter. Beyond the rhythm of orbits, there's a slower, more subtle dance called secular resonance. This doesn't involve the orbital periods themselves, but the precession of the orbits. Think of an elliptical orbit drawn on a page. Secular precession is like slowly rotating that whole ellipse. When a small body's orbit precesses at the same rate as a giant planet's, it's in secular resonance. This can pump up the smaller body's eccentricity over millions of years. A specific secular resonance with Saturn, known as the Nu-6 resonance, is thought to be a primary escape route for asteroids, pushing them onto paths that cross Mars and even Earth, turning them into potential near-Earth asteroids. Then we have spin-orbit resonance, which is a relationship between how fast a body spins on its axis and how long it takes to orbit another body. The most famous example is our own Moon. The Moon is tidally locked to Earth, meaning its rotation period is the exact same as its orbital period. It's in a 1:1 spin-orbit resonance, which is why we always see the same face. This happens because Earth's gravity creates tidal bulges on the Moon, and the friction from these moving bulges over billions of years slowed the Moon's rotation until it locked in place. A weirder case is Mercury, which is in a 3:2 spin-orbit resonance. It rotates on its axis exactly 3 times for every 2 orbits it completes around the Sun. Finally, there's the Kozai resonance, a complex tango between an orbit's tilt or inclination and its shape or eccentricity. In this mechanism, An object in a highly tilted but circular orbit can be gravitationally nudged into a much more elliptical but flatter orbit, and then back again. This back-and-forth trade-off between inclination and eccentricity can have huge consequences for the long-term stability of an object's path. Perhaps the most spectacular example of resonance in our solar system is the Laplace resonance of Jupiter's Galilean moons. 3 of its largest moons, Io, Europa, and Ganymede, are locked in a precise 1 to 2 to 4 orbital chain. For every single orbit of the outermost moon, Ganymede, Europa completes exactly 2 orbits, and the innermost moon, Io, completes exactly 4. This resonant chain forces the orbits of the moons, especially Io, to be more elliptical than they would naturally be. As Io moves along its elliptical path, the strength of Jupiter's immense gravity varies, constantly stretching and squeezing the moon. This continuous flexing generates an incredible amount of internal heat through tidal friction, making Io the most volcanically active body in the entire solar system. This same process is thought to generate enough heat on Europa to maintain a vast liquid water ocean beneath its icy shell, making it a top candidate in the search for extraterrestrial life. All of this, from volcanoes to hidden oceans, is a direct consequence of orbital resonance. Even the beautiful rings of Saturn are a work of art sculpted by resonance. The most famous feature, the Cassini division, that huge gap between the main A and B rings, is created by a 2-to-1 resonance with the moon Mimas. Any ring particle in that gap would orbit Saturn twice for every 1 orbit of Mimas, receiving regular gravitational kicks that clear it out of the area. As we've seen, orbital resonance is a double-edged sword. It can be a force for stability, protecting bodies like Pluto, or a source of chaos, creating the Kirkwood gaps. When multiple resonances are close together, their effects can overlap, leading to unpredictable, chaotic behavior, where an object's fate becomes impossible to predict over long timescales. For years, scientists have wondered if our own solar system is truly stable, with some studies suggesting there's a tiny, but non-zero chance that Mercury's orbit could become unstable billions of years from now due to a secular resonance with Jupiter. With the discovery of thousands of planets orbiting other stars, we've found that resonance isn't unique to us. The TRAPPIST-1 system, for example, has 7 Earth-sized planets locked in a complex chain of mean motion resonances, allowing them to exist in an incredibly compact and stable configuration. Even more remarkable is the HD 110067 system, discovered recently. It hosts 6 sub-Neptune planets in a perfectly synchronized dance, a pristine chain of resonances that has likely remained undisturbed since the system formed billions of years ago. Studying these systems gives us a window into how planetary systems form and settle into their final architecture. Orbital resonance is more than a cosmic curiosity. It's a fundamental principle of celestial mechanics. It's the hidden harmony that dictates the structure of our solar system and others across the galaxy. It writes its story in fire on Io, in water on Europa, and in the ghostly gaps of the asteroid belt. It is a constant reminder that the universe, governed by the silent hand of gravity, is an intricate and beautiful symphony, a cosmic dance of stability and chaos that continues to unfold before our very eyes.